Hi everyone. So this is a wee kind of fill-in PowerPoint video about a property of light, and it comes under the waves and radiation unit. It's called refraction. Now, you may have done some of this in third year, depending on what teacher you got, and you might also have done a bit of this in S2 physics, S2 science. Okay, so um, here it's an animation that you're going to see about the change in light, speed and wavelength when light travels from one um, object to another. So it's about light speed and wavelength, and here we've got a ray box which is going to send out a beam of light at the speed of light. Now clearly that's been slowed down for the animation purposes. And now what we're going to do is put a second ray box position, so it's going to shine the light ray through a glass block. So the first ray box is going through air, and the second ray box of light is going through the glass. And you can see when it goes into the glass, it slows down, which is what you would expect, the glass being a bit more dense than the air. And in fact, it slows down to about 2/3 of its actual speed in air. So it's about 2 times 10 to the power 8 meters per second in glass. The exact speed would depend on the type of glass it is. Now this next one looks a wee bit confusing. This red vertical line here represents the crest of a wave, and the pattern of these red lines are the wave fronts, and they're going to go from left to right and they're going to pass through the glass. Now hopefully you can see that in the glass the wavelength, the distance between the wave fronts gets shorter, and so the wavelength decreases in the glass. So the distance between the wave fronts, which is the wavelength, decreases, and then when it leaves the glass at the other end, the wavelength increases again. And to kind of summarize this, the learning outcome you need to know is that the speed and the wavelength of the light in glass are smaller than they are in air, and the same is true for water or any other substance that light might travel through, and it will slow down. And this effect of the light slowing down and changing its speed and changing the wavelength, decreasing the wavelength, is called refraction. So this next slide is kind of my made up one, just to kind of summarize what we've just been doing on the animation there. So if you've got a beam of light going into a glass block and it's going straight into the glass block, not at an angle, then it slows down to about 2 times 10 to the power 8 meters per second when it's inside the glass, and then speeds up again when it leaves the glass. And this property of the change in speed is called refraction. And that's just repeating what I've just said. Light travels from air into a glass block, it slows down, but then speeds back up again when it leaves there. So this diagram, the blue lines represent the wave fronts, and the distance between the wave fronts is the wavelength. And so you can see, there's no animation here, but you can see hopefully that the distance between the wave fronts after the glass block and before going into the glass block is bigger, so the wavelength is bigger and the wavelength decreases inside the glass block. And so the distance between the blue lines is the wavelength, and the wavelength in glass is smaller than in air. So the two learning outcomes from this is that the speed of light in glass is less, and the wavelength of light in glass is also less. So that's the first learning outcome you really need to be aware of. So the next one is a bit of a more complication about what happens when light isn't just going straight into the boundary of the glass, it's going in at an angle. And this looks a wee bit confusing, but I'll explain it on the next slide as well. So we've got this vertical line here that's going to represent the wavefront. Hold on, I better press play. So this is to do with the change in direction. Now there's some weird optical effects that happen because of this. I'm not going to go into them today, but it's basically because of this, that light, when it enters the glass at an angle, it can change direction. That was a bit of a misstart there. So these are the wavefronts, and when they go into the glass block, the bottom part of the wavefront hits the glass block, slows down, and then the top half has to kind of catch up with it, and that leads to a change in direction. It's easier to explain and look at it if we just look at this purple line. The purple line shows the direction of the light ray, and you can see it changes direction inside the glass block and then changes direction on the way back out the glass block. So the purple line is kind of the important bit. There's another explanation of why it changes direction. But basically, this change in direction is due to the change in speed. Now, the change in direction isn't refraction. It's due to the refraction, but it's not the definition of it. So I've turned on the trace of light. Now, the green dotted line in the first boundary is called the normal. And it's a right angle construction line to help with understanding what happens to the light ray. So the angle of incidence I shown there is bigger than the angle of refraction, because when light enters the glass block at an angle, it bends down towards the normal inside the glass block. And so the angle of refraction is much smaller in this case. But if you look at the next boundary, it does the opposite and bends away from the normal again. So if this is the normal here, and there's your angle of incidence, there's the line, the light beam going into the glass block. And if there was no glass block there, it would carry on along here somewhere, but you can see it bends down towards that normal inside the glass block. That angle I is called the angle of incidence, and the angle R is called the angle of refraction. So in this slide, it's really just going to summarize that last slide, but without the animations, okay? So instead of tilting the glass block, all I need to do is put the light ray into the glass block at an angle, and you can see that it changes direction inside the glass block, and then it changes direction back again. Now, the thing to remember is this first light ray and that last light ray would be parallel to each other. So all that's happened is the light ray has been deflected offline a bit. So there's your normal, both normals this time on both surfaces. Remember, the normal is just a construction line. It's not actual light or anything like that. It's just a line to help you with the angles. And it's at right angles to that boundary between the air and the glass. And the same thing at the other surface. Remember, this angle between the light ray and the normal, angles in physics are always measured between the ray and this normal. And so that's your angle of incidence. There's the angle of refraction. And going from air to glass, or less dense to more dense, the angle of refraction is always going to be smaller than the angle of incidence. So to summarize all that, when light travels from air into glass, it enters the glass at an angle. Angle I is the angle of incidence. And the light ray changes direction and it bends down towards the north. So explain that again. So if there was no glass block here, if you imagine this light ray carrying straight on, it would end up here somewhere, but what happens is it bends down towards the normal inside the glass block. And angle R is the angle of refraction, which going from less dense to more dense is always smaller than the angle of incidence. And the opposite is true when the light ray leaves the glass block at this surface here. It bends away from the normal, because if you imagine that's the light ray, if it was going straight through like that, it would just keep going like that, but what happens is it bends away from the normal. That's going from glass back into air. So that's it, short and sweet, and I'll catch up with you when you get into class.